So we've begun to scratch the surface of how we might think about work and heat on a molecular scale. What I want to do now is, I hope a little bit fun, but I want to think about what sort of indicators would we look for in a molecular system that would be an indicator of entropy change or an indicator of enhanced entropy. So in the earlier segment, we said we would equate an incremental change in heat with something that would amount to looking at incremental changes in the probabilities or the distributions of those molecules among different states. Now I'll remind you that an earlier result we had for an incremental or a differential change in entropy was that it was the incremental change in reversible heat divided by temperature. So if I begin now to pull these things together, this would be 1 over T times the sum over the energies d pj, where these pj's are the probabilities. So what we're saying here is that somehow this incremental change in entropy connects over here to incremental changes that are being made in the state distribution, incremental changes in the probability of observing certain states. Now, another clue that we have is that we have talked about for spontaneous processes that we tend to see in an isolated system that the change in entropy must increase. This is an indicator of spontaneity in those systems. So what exactly does that mean? Well, if we're increasing ds, we must be increasing somehow probabilities of certain states. All right, but the way we're increasing probabilities of states that we've learned in looking at the whole issue of state distributions is to maximize the number of microstates they have available to them. So remember, when we were looking at state distributions in Module 2, we found that the most probable distribution was the one that had the most microstates. So in other words, state distributions in some sense are optimizing or maximizing the number of microstates that they have available. Well, I guess our underlying question here, or at least what I'm trying to hint at, is perhaps this is somehow tied to this notion that entropy is maximizing itself for spontaneity. So maybe somehow entropy is tied to this optimization of the number of microstates. Let's pursue this a little bit further. Let's suppose we have a system of translational states, and we know that they have certain energy levels. And now we increase the volume. What happens to those states? Well, when we increase the volume, remember the energy levels went as h squared over 8m L squared. L squared is like volume raised to the 2/3 power. So increasing the volume is increasing the size of the boxes that they're in, which is increasing this parameter. So we're bringing the energy levels actually closer together when we increase volume. If we were to increase it again, we could bring them together much closer together. Well, now what's happening here with the number of microstates? Well, with a system, as we bring the energy levels closer together, there turns out there are more different ways that we can arrange the molecules among those states that are equivalent, that have the same total energy when you add them all up together. So by increasing the volume, in a sense, we can say we have increased the number of microstates that are available to that system. This was also true when we looked at the partition function for translation. Remember, the partition function for translation could be related directly to the volume, because this was the expression for it, and it was times volume. So as we increase the volume, we're increasing the partition function, which means we're increasing the availability of the states. So somehow volume increases microstates, and if that is tied to entropy, then we would expect that a volume increase would increase the entropy. Well, is there a way we can test this out? We know that when we go, say, from a liquid to a gas, I'll say a liquid to a vapor, that the molar volume in this case increases. Does that mean that the entropy of a vapor is greater than the entropy of a liquid? It absolutely is. In fact, that's one thing that we can say without reservation, that a vapor tends to be much more entropy filled than a liquid. The same is going to happen when we go from a solid to a liquid. Now the volume change isn't as great in most cases here, but there is some volume change, and it's typically an increase in the volume. So we'll find that the entropy content of a liquid is also going to be greater than the entropy content of a solid. So we see a uniform increase as we move from solid to liquid to gas, and that also corresponds to an increase in the volume. So at least that meshes with our expectation now. What about temperature? Well, we've also seen indications that temperature also increases the availability of states. So let me remind you of what the Maxwell-Boltzmann distribution for velocities looked like. So this was the probability of velocities, and at low temperature it was a peak distribution that was peaked very close to zero velocity down here. And so this is low temperature. If we increase the temperature, we would get a distribution that was a lot more spread out. All right, well, what does this have to do with microstates and entropy? Well, here we see that there's all these states out here that now are more heavily populated. We haven't stopped populating states down in this end of the velocity distribution, but we have measurably increased the number of states up here. In effect, we have increased the number of microstates available to the system by increasing the temperature. All right, and this is in general going to be true for these systems, and you can see it would also be true here. As we increase the temperature, we increase the partition function for translation, so again we would be increasing the microstates. Now, do we see this for entropy? Well, I can draw a picture of what entropy looks like as we increase the temperature, and we've seen this for enthalpy but not for entropy. As we increase the temperature for a substance, we find that its entropy increases, very gradually at first. Then there's a jump. Then it increases more. Then there's another jump. Then it increases more. So this is what the entropy looks like as a function of temperature. So again, we see that entropy is increasing as we increase temperature. And of course, these jumps are of course related to melting here and vaporizing here. So we're making transitions from a solid to a liquid state, and then from a liquid to a gaseous state up here. And each time we do that, we are increasing the entropy. So this again ties in with this sort of hierarchy that we've seen here. So increasing both the volume and the temperature has a tendency to increase the entropy. Now, one last thing, and again I'm going to sort of call upon this this partition function as my guide for this. I know that if I have heavier atoms, so in other words, I'm increasing mass. Mass is here. If I increase mass, I'm increasing the number of states available. If I increase the number of atoms, well, remember that the system partition function goes as z to the n over n factorial. But the net effect of this is to greatly increase the number of available states. And so I think we can generally say that if we include more atoms in a system, we're going to increase the microstates available to that system. And we will also increase the entropy, since the entropy is going to be an additive quantity of all of those different parts. Finally, if we have a mixture, it turns out there are more different ways that we can mix the energy levels for such a system, so we tend to see that this also increases the entropy content, and that's something that we'll explore much more when we get to Module 5. But in any case, all of these things serve to increase not only the number of microstates, but also to increase the entropy. So our bottom line for all of this, and maybe I ought to put this in a special color, our bottom line is that when delta S increases for a spontaneous process, that this is tied somehow to an increase in available microstates. So whenever we can anticipate that something that we're doing is going to increase the available microstates, we can pretty much assure ourselves that we're probably increasing the entropy as well. And so another way to think of the second law of thermodynamics now is to say the universe entropy always increases in a spontaneous process. So in a sense, the universe is always attempting to maximize its microstates, maximize its probability.